Alright, let's talk about hydrostatic forces on planar surfaces. If we have a large container filled with fluid, say like a pool or a dam, the pressure in that fluid increases with depth, as we know by the equation gamma h, and it increases linearly. So if we look at the pressure on one of the side walls of that object, we can see that it increases linearly with depth. Now, what if we had like a gate or something on the surface of that container that we wanted to calculate the pressure of? I'm going to pull that out, and the pressure distribution on that surface can be described by a geometric object called a pressure prism. So that describes the pressure. There's some pressure at the top and some pressure at the bottom that's higher than that, and it increases linearly between the two. What we want to do in this module, or this chapter, is to separate that distributed pressure, or that distributed force, into a single resultant force. So this is just sort of a shorthand. This is a way of expressing that prism as a single force acting at a single location. We call that the resultant force. And as you can imagine, it's just the average pressure times the area of that surface. Now, incidentally, we're going to come up with an equation for this, which we're going to use, but you can also determine that total force simply by determining the volume of that pressure prism. So that's another way to solve this, and the textbook goes through that in detail. I'm not going to do that here, but just so you know, you can just solve it both ways. So the average pressure across that surface is the pressure at the top plus the pressure at the bottom divided by 2. That's because it varies linearly, and you can see that gives us this expression for our resultant force. We can rewrite that in terms of the distance from the water surface to the centroid of the object, hc, and when we use that instead, we can replace that equation with this new one, or the resultant force is gamma hca. And this is the equation we're going to use. So to find the pressure that, to find the resultant force that's acting on that submerged planar surface, a flat surface, it's gamma times hc, the distance from the water surface to the centroid of the object vertically, times the area of that object. So that is how we calculate the force, the resultant force on that object, and we use hc, the vertical distance to the centroid. But something to note is that it doesn't act at the centroid. If you remember, we have this pressure prism, and the pressure is greater at the bottom than it is at the top of the object. Because of that, the force is skewed downward. So the force actually acts at a lower distance than the centroid. We call that the center of pressure, and it's the distance. We're going to use YR to describe this, and YR is the distance from the water surface to the center of pressure. We're going to define it a little bit differently. This is in the direction of the planar surface. So when you use Y's for the rest of this module, that refers to in the direction of the object. And we'll return to that later. Right now the object is oriented vertically, so it's easier. Okay, so the equation for where that force acts, how to determine YR, is a function of the moment of inertia of the object divided by YC, which is the same as HC in this case. It's the distance from the water surface to the centroid, but technically it's in the direction of the planar surface, not the vertical distance. So, but again, in this case, since it's oriented vertically, HC and YC are the same. The moment of inertia, you studied that in statics. This is in the textbook here, these figures, and we're using IXC, and for a rectangular object it's that, and the location of the centroid is just halfway down, and for a triangle IXC is that, and if you remember, the centroid is located a third up from the bottom. So let's do an example using these equations. We've got this pool, let's say, or a tank, and there's a triangular gate on it. So I want to find the force that the water is imparting on that triangular gate where it's hinged at the bottom. Now keep in mind there's water in the tank. On the other side of the gate is air. So that's important to recognize that we've just got atmospheric pressure on the other side of the gate, but there's also atmospheric pressure pushing down on the surface of the water. So they balance each other out. Okay, so finding the moment, we need a force and a moment arm. So the force, Fr equals gamma hCa. hc is the vertical distance to the centroid of the object. So it's 8 meters down to the point of the triangle, and then it's 2/3 down from there to get to the centroid because we're working with a triangle. Area of a triangle is 1/2 the base times the height. And now we can solve for the resultant force. And we get 2,120 kilonewtons. The location of where that force acts can be calculated using the YR equation. First we need the moment of inertia. When you look it up for a triangle, it's BA cubed over 36. That works out to be 36 meters to the fourth. YC, since this is oriented vertically, it's the same as HC, so that's the distance, again, from the water surface to the centroid of the object, and is also 12 meters. Now we can plug and chug, and we get a YR of 12.167 meters. Okay, we've got a force. We still need a moment arm. YR is not the moment arm. For the moment arm, we need the distance from the hinge to the force. So that's that small distance upward. So to determine the moment, it's the force times the total distance from the water surface to the bottom minus YR. And that gives us our answer. Okay, so we've talked about this in terms of when it's oriented vertically. And HC equals YC. So HC is defined as the vertical distance. YC is defined as the distance in the direction of the object. Now, when it's angled, you can now see the difference here. So HC is the vertical distance from the water surface to the centroid of the object, whereas YC is in the direction of the object. So we just have to do a little geometry here. Also notice that the resultant force always acts perpendicular to the object. It doesn't act horizontally necessarily. It's always perpendicular to the surface because it's a pressure. So let's do an example. Let's say we have this goofy gate that's hinged at the top in this pipe, and as it's simply the weight of the gate itself. Say it's like an iron gate that keeps the gate shut. And if the water depth is deep enough, there'll be enough pressure to move that gate and allow water to pass underneath it. So we want to find the weight of the gate that's needed to hold back water that rises 2 meters above the hinge. So here's some information. Let's say it's a rectangular gate with the width coming out of the board is 1.8 meters. We've got an angle and a gamma for the water. So let's find the resultant force of the pressure pushing on that gate. So we can use that equation. HC is the vertical distance to the centroid of the object. So that's going to be 2 meters down to get to the hinge, and then another 2 meters divided by 2 times cosine theta to get to the centroid. So a little trigonometry there, but I'm sure you can work through that. Okay, our resultant force we then can calculate, and it turns out to be 98.8 kilonewtons. Where does that force act? We use the YR equation. First of all, we need our moment of inertia, and when you look it up for a rectangle, it's BA cubed. Now notice that this is the flat object. We don't have to do any trigonometry here. Doesn't matter how it's oriented. It's the size of the object. We need YC. Now this is in the direction of the gate, so we have to do some more trig. We've got 1 meter to get from the centroid of the gate to the hinge, and then we've got to get from the hinge up to the water surface. And that requires using cosine theta, dividing by cosine theta to get to the top. Now we've got all the numbers. We can determine the resultant the location of where the force acts at 3.595 meters in the direction of the gate. So we've got two forces. We've got our resultant force and we've got the weight. Weight always acts vertically. So now we just have to balance our moments and solve. We need moment arms. So the moment arm for the weight is that distance. For the resultant force, it's that distance. The moment arms have to be perpendicular to the forces themselves. We balance those and we've solved our problem. The first moment arm takes a little bit of trig again. It's 1 meter on the hypotenuse there. So L1 is then 1 meter sine theta. L2 is the distance from the hinge to where the force acts. So that's YR minus that distance that it takes to get from the hinge back up to the water surface. And now we've got all our information and we can solve for the weight of the gate. One last thing I want to close with here. This is all in the FE handbook, but it's a little murky. So I want to expose you to it so you know how to make use of the FE handbook. First of all, there's a typo in it. That alpha should be a theta, which is kind of obvious because alpha is not used anywhere else in this section. So that should be a theta. It also appears somewhere else. It should also be a theta where else it appears. Now we're looking for our force equation, gamma HCA. The FE handbook lists it like this, which I think is really stupid, but whatever. It lists it first as FR net, and the net refers to there being air on the other side of the gate. They first express it assuming there's a vacuum on the other side of the gate, which makes no sense to me at all. But anyway, so this is the equation that we're using. Gamma is rho g, and it has YC sine theta. YC sine theta is the same as HC. So you can see this is the same equation. And then where it acts, the YR equation, they use YCP, which actually makes a little more sense. That's the distance to the center of pressure. And everything else in there is the same. It requires a moment of inertia. That's also in the FE handbook in the statics section. And it's identical to what you have in your textbook.